Hello everyone, my name is Renhan Sun from Nonlinear Controls and Robotics Lab at University of Florida. Welcome to my ACC presentation, and the title of my talk is A Switched Systems Approach to Unknown Environment Exploration with Intermittent State Feedback for Nonholonomic Systems. Before I start the control objective section, I want to give you a brief explanation of the differences between the non-holonomic and holonomic systems. Here are some non-holonomic examples: ground vehicle, wheel mobile robot, and unicycle. As you probably can tell, these examples cannot move horizontally directly. In order to move sideways, they need to move forward or backward as well. The non-holonomic systems have velocity-dependent constraint conditions, and holonomic systems do not. The control objective is to enable a non-holonomic vehicle to explore an unknown environment where feedback is unavailable by intermittently following a trajectory through the unknown environment and intermittently into regions where feedback is available. As shown in the figure, the black rectangle represents the unknown environment the non-holonomic vehicle tries to explore. The black circles represent multiple feedback zones the agent can acquire feedback. The dashed line represents the desired trajectory the agent is tracking, and the solid line represents the actual path the agent traveled. It comes to the question of why do we care about non-holonomic systems? Why are they important? The proposed method can be applied in a wide range of applications, for example, mobile vehicles. The method can guarantee loop closure, which is what traditional SNAP methods do not have. The approach can be implemented in feedback-denied regions, and while the agent is in those regions, the overall system is stable under intermittent state feedback. In order to achieve the control objective, there are some assumptions. First, the system disturbances can be upper bounded by known positive constants. Second, there are multiple stationary known feedback zones in the unknown environment. Each of the feedback regions is defined by a compact set. Third, the non-holonomic vehicle is initialized in a feedback region. Fourth, the feedback regions are adequately spaced so that a vehicle can move between the regions while satisfying the subsequently defined dwell time conditions. The feedback region's locations cannot be too further apart, otherwise the agent will be lost in the feedback denied region and will not be able to accomplish the objective. Fifth, the desired states and time derivatives are bounded. Last, the maximum velocity of the non-holonomic agent can be upper bounded by a known positive constant. The agent can only go so fast, and this will prevent Zeno behavior. This is a kinematic model for a unicycle with an exogenous disturbance. XY denote the linear or planar position. Theta denotes the orientation of the non-holonomic vehicle. V1 is the linear velocity and V2 is the angular velocity of the agent. D represents the exogenous disturbances. QD and VD represent the corresponding desired state and velocity. There are three error systems have been defined in this paper. The trajectory tracking error E denote the difference between the true state and the desired state. The estimated trajectory tracking error E hat denote the difference between the estimated state and the desired state. And the state estimation error E tilde denote the difference between the true state and the estimated state. Note that E is equal to E hat plus E tilde, where Q hat denotes the estimated states, and the agent will use the estimated states when feedback is unavailable. To facilitate the subsequent unified control synthesis and stability analysis, these two global invertible transformation matrices are defined, where the auxiliary tracking error signals are defined as the corresponding stacked vector. Taking the time derivative of the previously defined signals, and then the open-loop error systems can be obtained as shown here. J is the constant skew-symmetric matrix. Fe and Fe hat are auxiliary signals defined as shown. UE and UE hat are auxiliary control input, and Chi1 and Chi2 are used to compensate for exogenous disturbances. The auxiliary control inputs are defined as shown, and TE and TE hat can be defined as shown here. Substitute in the T matrices into the auxiliary control input UE and UE hat will get the actual velocity control input V, which are circled in red here. To facilitate the closed-loop error system development, some auxiliary signals are defined. The specific expressions can be found in the paper. Due to the time constraint, I will not explicitly show them in the presentation. So the closed loop for trajectory tracking error and estimated trajectory tracking error can be obtained as shown inside the red rectangle. To integrate the switched system in the analysis, here are some definitions. Let phi be a switching signal, where A indicates the feedback is available and U indicates feedback is unavailable. Let TIA denote the time of the ith instance at which phi is equal to A, and let TIU denote the time of the ith instance when phi is equal to U. The dwell time of the ith instance of each subsystems is defined as delta TIA and delta TIU respectively. When phi is equal to A, a reset map is used to update Q hat T to be QT. However, when phi is equal to U, the state is estimated using the predictor in Q hat dot, and the closed-loop error system must be used for analysis to develop the subsequent dwell time condition. To develop the maximum dwell time condition, the time derivative of the state estimation error must be used, and it can be written as the expression shown. The stability analysis will have four theorems. Theorem 1 proves the stability of the trajectory tracking error ET when feedback is available. Theorem 2 proves the stability of the estimated trajectory tracking error E hat T when feedback is unavailable. Theorem 3 proves the stability of the state estimation error E tilde T when feedback is unavailable by satisfying the maximum dwell time condition. And Theorem 4 proves the trajectory tracking error ET is decreased below a user-defined threshold by satisfying the minimum dwell time condition. And additionally, Zeno behavior is excluded to prevent infinite switching. Here is the statement of Theorem 1, and it shows the trajectory tracking error ET is globally uniformly ultimately bounded. To get the result of Theorem 1, here is the flowchart of the process. First, we select a candidate Lyapunov functional VE, and then takes the time derivative of VE and get VE dot by substituting in the closed-loop error system, then invoking the comparison lemma to get an expression of VE. After that, we define a composite error signal ρe, which includes WE and ZE tilde, and ρe can be upper bounded. Using the relationship of ZE tilde is equal to ZDE minus ZE, we can upper bound signal ZET. Then we use the inverse of the state transformation matrix and signal chasing method. Specifically, we can go back through the open and closed loop error systems and control laws, and we can prove that all the closed loop signals are bounded. Therefore, the trajectory tracking error ET is globally uniformly ultimately bounded. Then, we can get a similar result for the estimated trajectory tracking error in Theorem 2. Similarly, the Lyapunov stability process are almost identical, except using the estimated states instead of the true states, and the estimated trajectory tracking error E hat t is proved globally uniformly ultimately bounded. Before going to the third theorem of the paper, I want to introduce a definition of maximum dwell time. A maximum dwell time indicates the maximum time an agent can operate without state feedback. As shown in the figure, the red solid line represents the maximum dwell time in between the time instances TIU and TI plus 1A. And theorem 3 shows the maximum time the agent can explore outside of the state feedback regions. Both EM and ET are user-defined parameters. Here's the flow of proving theorem 3. It's important to note that when feedback is unavailable, the state estimation error E tilde is exponentially growing. In order to bound E tilde, EM is introduced. By using the user-defined value EM, the maximum dwell time can be calculated using the relationship of E, E hat, and E tilde. Before reaching the maximum dwell time, the agent has to go to one of the feedback regions to update the estimated states. It's important to show that Zeno behavior is excluded. In this expression, dk is the actual distance the non-holonomic agent traveled in between the feedback regions. Vmax is the maximum velocity of the agent. Also, this is an assumption we previously made. By lower bounding delta TIU with t travel, Zeno behavior is excluded. Similarly, a minimum dwell time indicates the minimum time the agent must stay inside a feedback region to compensate for accumulated error. As shown in the figure, the red solid line represents the minimum dwell time the agent has to dwell in between time instances TIA and TIU. Similar to Theorem 3, Theorem 4 shows the minimum time the agent needs to dwell inside one of the feedback regions to compensate for the accumulated error, so that the closed-loop error systems are globally uniformly ultimately bounded. Using the upper bound on ET from Theorem 1 and define a lower threshold ET, then the minimum dwell time can be solved as shown here. This inequality is used to ensure ET converges within the desired neighborhood, and at the same time, Zeno behavior is prevented when feedback is available. To summarize the presentation, we have shown that the unknown environment exploration objective for non-holonomic systems under intermittent state feedback is achieved. The overall system is stable via a Lyapunov-based stability analysis, and Zeno behavior is excluded. The future research of this topic will focus on the development of optimal path planning, so the agent can explore optimally with limited feedback regions. In addition to that, we will incorporate a deep learning approach to train image data to get state feedback. That's all. Thank you all for listening, and please contact me through this email if you have any questions.